up?
Just batteries broken, or not batteries broken, this tag doesn't broken. I just changed the batteries in it, it's not turning off. And you said you wanted those, so.
Yep.
Like, because when I tried to join it, my school was on Assembly Street.
Yeah, I can't get into it. Really? Weird.
Maya Glenn to the front office, to Maya Glenn.
Oh, yeah. That was the first one, getting your seat. Yeah, you want this?
This interruption. The Health Science Academy kids will eat first lunch today. Gaston College will be here to talk about registration for next year. So for today, Health Science Academy students will all need to eat first lunch, and then we'll report to the auditorium. Thank you.
Yeah, that's embarrassing. But it said you like 80 the whole time. I would say it's maybe
Yeah, can you see the desk that way? Yeah? Yeah. How do I do that? Pre-med. That's today's warm-up problem. How did the live stream go? Let's see our homework. Let's get it out.
So you, yes, okay.
You want to start with what you put as a default?
I'm ready to do it on Friday. You just got into the instead. No, I don't have any six. Cool.
Henry. Okay. So. I think we're gonna have to talk with TSS, which are our, technology people. I forget what it stands for, to be honest, but I know T stands for technology. I don't know what the other two S's stand for. So you guys couldn't get into the live stream through your school Gmail accounts. No. Okay, so that's probably something to do with the restrictions on your school Gmail account, where you're probably not allowed to attend live streams with it. So I'm not super surprised. I'm gonna wonder if I can get that lifted for you all. Something that I'll talk with Ms. Reed about and see, because since we are an experimental trial group, see if we can get that changed. Other than that, how did it go?
Pretty good. That's good. I like that.
It's not being in class, but is it better than videos?
Yes. Still more hands-on than just watching video.
Like actually here? Anybody other than John and Brian have opinions?
I think I like the videos because I can like go back
Mhm.
and catch up, but that's like,
Did you see that these store on my YouTube, so you can go back and rewatch them?
It's just that the videos are more like to the point, I guess.
Right.
And also, you know, like what slides on the videos, what slides you're on. It's hard to
Yeah.
know on the live stream which slides you're.
So overall, we're gonna do all of Unit 3 like this, okay? But I'm gonna leave it up to you guys if we're gonna keep doing it or not doing it, okay? If you guys wanna go back to the way it was, then so be it. If we wanna continue doing it this way, that's also fine. I will tell you that this is less work for Mr. Kaufman. It's significantly less work for me. Because rather than having to pre-record a video, I'm recording video while I teach it. So that does help me, but I do understand your point of it can be a little bit difficult to keep up on which slide we are on because I can't do the slides on the stream. I try to say, but of course that gets away from me from time to time. As well as you're right. I mean, the videos are right to the point because they have to be, because Loom has a time limit of 35 minutes as recording. And sometimes we push all the way up to that limit. So that's why they are that way. But yeah, we'll continue to see how it goes. And today's really kind of a big question day to see if you guys are actually ready to do what we got to do today. Because if you didn't attend live streams, you didn't understand Thursdays and Fridays, today's is not going to make any sense at all. Likewise, when they come back on Thursday, if they don't keep up, Thursday's lesson will not make any sense at all. So, speaking of things making sense, you all didn't have any homework questions that I'm aware of on 3.1. Do we have any homework questions that we would like to ask about 3.2? If you had homework questions on 3.1, my response to you is why didn't you ask them on Friday? Caleb, Dom, you guys are way back there. Can you guys see okay? All right, you let me know if you can.
17.
17, 3.2. Anybody that's watching on live stream that has questions, you go ahead and type them there in chat as well. John?
31.
31. (17) and 31. I'm trying to break my neck over this boards. Fatima would like to do number 59. So we'll throw 59 up there as well. Okay. let's jump into it here. Let's start with 3.2. And let's start here with number 17. Number 17, we're going to use Rolle's theorem. We're going to talk about whether or not it can or can't be applied. And then if it can be applied, we're going to find the value of C here that we are interested in. So what's the criteria for Rolle's theorem? What's the things we got to show? Go ahead, John.
It must be continuous.
Got to be continuous. What else? Go ahead, Parker.
Differentiable.
Differentiable. Anything else for Rolle's theorem?
Don't the endpoints have to equal the same?
Endpoints have to be the same for Rolle's. Now, it's not true for the mean value theorem, right? So they are different beasts between the two. So when we look at number 17, we're looking at f of x is equal to, we got x squared minus 2x minus 3 all over x plus 2. And we are running this interval from -1 to +3. So -1 to +3. So for us to test Rolle's theorem, let's put our answer key up here for us on the board. That way we have it. Do so. We're working this out right here, 17. Okay, so let's start with, is this continuous on this interval? Will it be continuous from -1 to 3? What's the only point that we need to worry about discontinuity with this function? Where's it going to have a vertical asymptote? Or a hole in the graph? At -2, right? That's the only time that we got to worry about this, whether we factor this out and try to take it there, which if we do factor it out, that's not going to actually cancel out with our x plus 2 group. We should get x minus 3 and x plus 1 if you factor this out, okay? So that's not going to be an issue there. That's not going to be an issue there. It's not going to get rid of it. So we are going to be looking at a vertical asymptote at -2. Of course, that's not an issue here. We're picking this up on the right side of the graph here, so it should be continuous. Is it going to be differentiable between those points? Think about a rational graph. Think about its shape. It should be differentiable along that point. There's no sharp points and no other breaks in the graph that we need to worry about, right? So that's really kind of the first two questions there. Is it continuous? That's going to talk about any breaks in the graph. And then the next part about being differentiable, the only other extra thing we need to worry about is, of course, if it comes to a sharp point, like an absolute value, right? So neither one of those are happening here, so we are continuous through there. So the next thing we need to show is that the endpoints, of course, are going to be the same. So when I plug these in, as I just told you a minute ago, if you do take the time to factor out this numerator, you'll find that you're going to get x plus 1, x minus 3, all over x plus 2. And that these are, in fact, the zeros to the top here, correct? Which will make the whole thing go to 0. So f of -1 is 0, f of 3 is 0. So Rolle's theorem does, in fact, apply. What does Rolle's theorem then tell me? What's going to happen between -1 and 3? Go ahead, Adam.
There will be a derivative of 0.
There's got to be somewhere in between -1 and 3 where my derivative reaches 0. AKA, there has to be a maximum or a minimum somewhere between these two. Some x value that creates 1 for us, right? Okay, so let's go ahead. Let's get our derivative then. This is best done, of course, here with a good old-fashioned quotient rule, f and g. When I take the derivative of f here, we're looking at 2x minus 2. When I take the derivative of g, we're just looking at 1. We all okay there? So we'll set up our standard quotient rule. We're going to have g squared. We have g times f derivative. g derivative times f. What is this going to give us? It's going to give us x plus 2 quantity squared. G here is x plus 2 again. We're going to multiply that by 2x minus 2 minus, and then we're pretty much going to keep f's the same here because it's just getting multiplied by a 1. So this is what we're looking at here. We are going to reduce this down a little bit more. We need to go ahead and FOIL this out. Question? Sorry. Thought I heard something. No? Okay. Let's go ahead. Let's FOIL this out. 2x squared. And that's going to be minus 2x. Then we have plus 4x. And then minus 4. And I'm going to send all of this in right now. Make sure you take the negative with it. Because if I'm going to combine like terms after FOILing, I might as well combine all the like terms. All over x plus 2 quantity squared. Okay, let's go ahead. Let's get our x squareds down. That's going to give us a singular x squared. I got negative 2x plus 2x. Those cancel. I got plus 4x left. I got minus 4 and plus 3, so that's minus 1. All over x plus 2 quantity squared. Are we all okay so far? Questions here, issues here, meltdowns here. We're all good. Okay, so the next part of this course is to find where this derivative is going to equal 0. What do I need to worry about for that? What am I going to set equal to 0? Go ahead, Mikhail. Just the numerator. I'm just going to worry about just the numerator here. Because denominator is going to give us an undefined value. First off, that's going to happen at negative 2. We can all see that pretty easily. And negative 2 is not even in my integral, just like it wasn't in the first place. We're going to focus on this part right here. Just the numerator. 0 is going to be equal to x squared plus 4x minus 1. Is this going to factor? Take a look at my answer key. Does it factor?
No.
Nope. Good old friend quadratic formula then. Negative b, so negative 4 plus minus square root b squared, which is 4 squared, minus 4ac, which is 4 times 1 times negative 1, all over 2a, so 2. It's going to be negative 4 plus minus, that's going to be 16 plus 4, all over 2. That's going to be negative 4 plus minus square root 20, all over 2. It's going to be negative 4 plus minus 2 to root 5. 2's cancel. Negative 2 plus minus root 5. Those are my two answers. My two answers. Are we all okay so far? Are we all okay so far? The next step here is, of course, to make sure that both of these will occur in this interval. So, calculate. Where did I put it? I'll just grab this one right here. Nope, I don't want to grab that one. That one's broken. I'm going to go get my other one. So, negative 2 plus square root 5. That gives me 0.236, which is in my interval, so the positive version is good. Let's try the other one. Negative 2 minus square root 5. That gives me negative 4, which is not in my interval, so only the positive version here is the one we are looking for. Questions? Number 17. Let's move along. Let's take a look at number 31. So for number 31, copy the graph and sketch the secant line to the graph through the points A, B. Then sketch any tangent lines to the graph for each value. This is really just more just drawing than it is anything else. I'm actually going to refer back to my answer key. I'll try my best to redraw it for those of us at home. But if you're looking at number 31, there's my secant line between the two, right? And then you might be, I don't know if you can see because it didn't come in very clearly, my tangent line right up at the top. So I'll do my best to recreate up here. So we have here, it dips down, and it curves up, and then dips down again. And then at this dip, somewhere over here is A, and somewhere over here is, actually it's more down, it's more like right here, is B. So the secant line runs between the 2 points like that. So this is my secant line. The tangent line is going to be anywhere that hits a critical value. So my tangent line is up here, it's given the top of this max right here. So this is a tangent up here. Questions?
Would there be a tangent at the minimum as well?
Would be a tangent at the middle one as well. This one right here?
Yeah.
Yeah, there should be. Is there not one on there? Yeah, well, you can, there's a little, very, very baby little one right here. I think maybe only Parker can see it. It's right there too, yeah. Anytime that we would have a maximum or minimum, yeah, Dawson, we would be looking at another tangent line. So right there. And that's really it. That's all we're looking for 31. Ms. Mazaka did a nicer job than I did. It's just that she didn't know to draw those out as dark or label them, which is, once again, probably my fault. Ms. Mazaka don't make mistakes. Okay, and then number 59, we're talking about the word problem here with the speed. That's a question Fatima wanted to do. I'm going to double check our chat here to make sure that we have any other follow-up questions here. Okay, so for number 59, this is very similar to what we did at the end of class on Friday. Very similar to what we did on the end of class on Friday with our little speed track problem. So the plane begins its takeoff at 2 p.m. on a 2,500 mile flight. After 5.5 hours, the plane arrives at its destination. Explain why there are at least 2 times during the flight when the speed of the plane is at least 400 miles per hour. So what we're going to go through here is we're going to look for the average speed. We're going to look for the average speed. So what we have here is 2 times. We have time 0, of course, when we start our flight, and then 5.5 hours later, right? Those are our 2 times, T1, T2. Now, the total distance traveled between those two is 2,500 miles. Agreed? What they've described. Okay, so that means over the course of the entire flight, we have traveled roughly on average for, 454, miles per hour. Okay? So that is my average time. So just to back up here a little bit, so we have our T1, 0, T2 is 5.5. So then we're looking at the average speed. Is going to be the distance traveled, of course, over that 5.5, which is where I'm going to get my 454.4 miles per hour. Is everyone okay with this so far? Everybody's good with our logic so far? John?
It's 0.5.
Is it 0.5? Not 0.4? My fault. Okay, so the question here is I want to prove that at least twice we got to 400 miles per hour, right? So let's logic our way through this. Let's try to use our different theorems, okay? So which one do you think we should use here? Are we going to talk Rolle's theorem? We're going to talk mean value theorem. Let's talk about which one we would like to apply. Is it Rolle's? What would Rolle's tell us? What does Rolle's tell us? I'm not trying to be sarcastic with you. What do we need? We need our endpoints to match for rolls, right? That's what we just did with 17, didn't we? Okay. And we need what else? If we're thinking about this as a function of speed, right? At time 0, we have 0 speed, right? We're on the ground. And then at final time, we're plane stopped, right? Shouldn't still be traveling. So seems like rolls might apply here. Rolls would also give us what? What happens between the two endpoints in rolls theory? A max or a min or more than that. It says at least one critical value, yes? Okay, what about the mean value theorem? What does that tell us? We don't need the endpoints to match there. We just need continuous and differentiable. What does it tell us? In so many words less, doesn't it say that there's some x value that represents the average speed over the time frame, right? Are we okay with this so far? So, when I look at this plane, it means that there's got to be at least one moment where the plane is flying 454.4 or 454.5 miles per hour. That is the mean value theorem. That at some point we reached this, right? That's our mean value theorem. That's what I have there in the first paragraph of my answer. Since the average speed of the plane is 454.5 miles per hour, then there must be at least a singular point in time where we traveled that speed. Does that make sense? Okay? If that means that I reached that speed at least once, this means that I might had to have flown up to 400 to get there and over 400 to balance that out. We started at 0 speed, right? Think about it logically, gang. We start at 0 speed on the ground. The plane starts to take off. We have to get to 454, which means we passed 400 on the way up, right? The plane is going to come to a stop again, right? Which means we are going to pass 400 on the way back down too. Does that also make sense? So no, I don't really need Rolle's theorem here because Rolle's theorem tells me the maximum and minimum speeds along the flight. That's not the question at hand. What we're looking at here is, if we're thinking about our graph, going back to that previous one, here's time A. This is time. This is speed. Okay? So somewhere along here, this is 400, and somewhere up here is 454, and maybe somewhere up here is 500. Okay? So at time A and at time B, we're here. Now, whatever happens between here is great and fine and all and dandy, but this right here is my average. And those of us in stats should know that if I hit this on the way up, I got to hit it on the way back down too. That I have to have an equal number above and below this marker for it to be the average. Questions? Okay. After today's lesson, this is where our first quiz for this unit is going to take place. I'm going to have it open up here later today. I didn't get it programmed in yet. Plus, I didn't want you to start it until you saw the lesson. I'm going to give you all day Wednesday in exchange for the later start date on it. So that's your only assignment you're doing on Wednesday. We're not live streaming, no video, no nothing. That's your deal on Wednesday to do your quiz. I know that in general, I am a little bit behind on grading, and I do apologize for that. Part of the reason why I'm doing live streams here to help me speed up that process too. So let's jump into what we're going to do today. The first derivative test, increasing and decreasing intervals. Things that I know, one, you have some experience with, and two, that you don't like to do. So let's talk about these. Let me check chat here, make sure that we don't have any follow-up questions. Seems like we're good. Okay, so we're going to move on to what would be, I guess, slide 3 of the presentation because the first one says quiz tomorrow. This one is the title slide, so I guess going into slide 3. So talking about increasing and decreasing. These are literally my slides from Math 2 to get us started. To rewind and go back in time a little bit. So, of course, we read the graph left to right. If the graph is coming up, then we are increasing. If the graph is going down, we are decreasing. If it flatlines, we are at a constant, which is neither increasing nor decreasing. And what we're going to do is we are going to talk about splitting up the domain for the x values that this is going to occur through. Okay? So, traditionally speaking, we would say negative infinite through infinite, but not anymore. We're going to say negative infinite through here, we are increasing or decreasing. From here through here, we're increasing and decreasing. Now, we are not going to actually include the points of switch because at that point, we are neither increasing nor decreasing, and that's where the first derivative test is going to come back into play. Questions? Okay, let's see how we do. Let's move on to our first problem, which would be 1, 2, 3, slide 4. So, nice little easy parabola for us. Nice little easy parabola for us when we're looking at this problem. I want to know when is it increasing, when is it decreasing? Who wants to help me? Go ahead, Luke. What do you got?
From the left, it's decreasing, it's going down.
Yep. Okay, so from negative infinite to where?
To -1.
We are decreasing. Is this okay the way I have it written?
No, I think it needs to be a parenthesis.
It is a parenthesis. I'm glad to know that you were paying attention when I just said that a second ago. Now, what led you to say -1, sir?
Because it stops at -1.
Because it stops at -1. That's where our minimum is going to occur. That's where our critical value is going to be, to go back to what we've been talking about Thursday and Friday. Right? So ultimately what we're going to do here with the first derivative test is going to help us do is going to help us find the critical values and then determine whether we're increasing or decreasing or rounding, which will tell us whether we have maximums or minimums. If you recall Thursday and Friday a couple of times, we had a problem where we gave a critical value and said we can't determine whether this is a max or a min without more information. Today we will know that more information. Luke, let's pick this back up here. Of course, we're going to be increasing after that, correct?
Correct.
And what's that interval?
-1 to positive, or to infinity.
Through infinite, and this is what we're looking at here for problem number 1. And I can't explain it more thoroughly than that because that is exactly my slides from Math 2. So if I can teach this to you all when you're freshmen and sophomores, we should be able to handle it now that we've ran the gauntlet of math classes and are back for round 2, 3, 4, possibly 5 for some of you. I don't know, you guys just like are masochists or something and just keep coming back for more punishment. Questions here? Let's move on to the next problem then. Another nice parabola for us. So this should be slide number 5, according to my thing. Okay. Any takers? Ryan? Might as well get them in now while it's easy, right? What are we doing, sir?
It is increasing from negative infinity to -3.
Absolutely. We're coming up, so we're increasing from negative infinite from -3.
And it's decreasing from -3 to positive infinity.
Very good. We're decreasing from that point down. Would be parentheses on everything just like the previous one, yes? Awesome. Okay, so let's move on to slide 6. Let's look at something that's a little bit more complicated than the standard parabola. So, when the function is increasing, what should we say about the derivative? If the function is increasing, what should you tell me about the derivative? Allie? That it should be positive. If it's increasing, we should have a positive slope, right? We should be moving upwards in the graph, right? Okay. What about when the graph is decreasing then? negative, right? That doesn't take a rocket scientist to figure that out. If it's increasing and positive, decreasing will be, of course, negative derivatives, right? Okay, and of course, we talked about this briefly, but we'll talk about it one more time. When the graph is constant, this should be 0, right? The only other points that we should be seeing 0 is at maximums or at minimums, right? Which, of course, means that, of course, the tangent line comes and skims right across, and it does so in a flat line. The only other time that that, of course, happens is, of course, if the function itself has flatlined. Questions? So this is inevitably how we're going to use and bring back our critical numbers and our first derivatives. So, as we're talking about this, remember that the first derivative represents slope. Since we're talking about increasing and decreasing, we're going to talk about the first derivative, how it reflects that, and how the slope reflects that, okay? We're trying to tie everything back together here. I'm trying to grab some things from Math 2, Math 3 curriculums and make you understand how they relate to what we're doing here in calculus. So, the first derivative test, and I just put this slide in today. Because I thought that maybe we just need a little checkpoint for this slide here with the first derivative test. Looking at slide number 7. So the first derivative test, what it's going to give us, what we're going to do. So if the graph is going to change from increasing or decreasing, it is going to happen at a critical value, at a critical number. Since these critical values represent different maximums and minimums, whether they are the absolute or relative, this is where the slope inevitably must change over. Actually, number 59 that Fatima asked us to do is a great example of that. If I'm going up to this point, then I have to go up to get there, and eventually I have to come back down. So if for us to reach a maximum or reach a minimum, we have to be positive or negative to get there, and then the opposite to go away from it. Because if we never switch over, we never have the peak of the hill, we never have the bottom of a valley, therefore we wouldn't have a maximum or a minimum. So the way we're going to do this, the way I like to do this, is I like to create a little number line based around these critical values and see what we'll do in a few problems. Where I'll get the critical values and they'll represent little key tick marks on my number line. And then I'll test a few numbers before and a few numbers after. And that'll tell me whether my slope is positive or negative. This will, of course, also tell me increasing and decreasing. This will also tell me whether I have a maximum or a minimum. A lot of really good, valuable information on this slide. This is pretty much everything we're going to do today in a nutshell. That's why I decided to put it up here, just to make sure it was all clearly stated, black and white, as plain as I could make it, as direct as I could, as to the point as I could. Because Luke, I might have anticipated that thought there, that these are a little bit roundabout sometimes, especially for those of us on live stream. I will say that if you ever get lost on what slide we're on, type it in there, type it in chat, and let me know, and I will try to reiterate. Okay? I'm trying to do a better job of that today, because I thought about that and how I could better do that. Questions here? Concerns? So we'll start with a few basic ones, and then we'll move into a more complex setting. Okay? So let's start with the graph. Let's move on. Slide 8 now. So I'm going to look at this graph, and I want to go ahead and apply this same idea of the first derivative test. So start by identifying the critical points, the critical values. So this is where all of our maximums and minimums are going to occur, right? I didn't give the function for this one, so that's why I listed them out. I have x here, negative 1.5, x is at 2, and x is at 4. We see that those are all relative mins or maxes or absolutes, right? We have an absolute min at negative 1.5. We've got a relative max at 2 and a relative min at 4. There is no absolute max for this function. Okay? So by highlighting those points, we should be able to highlight where we are increasing and decreasing. This is exactly what we were doing before, yes? Okay, so who wants to tell me increasing and decreasing intervals here for this function, for this slide? Go ahead, Luke. What are we going to do first?
The first one's a decreasing.
Decreasing?
From negative infinity to negative 1.5.
Negative infinite to negative 1.5. Parentheses on everything, right? Okay. You want to go in order, just continue to go back and forth between them?
That's fine.
Okay, so next?
It's increasing from negative 1.5 to 2.
Negative 1.5 to positive 2. After 2, what are we going to do?
Decreasing from 2 to 4.
From 2 to 4. And then?
Increasing from 4 to infinity.
Increasing from 4 through infinity. Questions here? Anytime we switch over between the two, that should represent either a maximum or minimum. So when I look at this, I should see 3 different points where I'm switching over between increasing and decreasing. I have right here, this is 1, this is at 1.5. I have another one here at 2, and I have another one right here at 4. Questions? I like to do this in a number line. I think that this way can sometimes be confusing. I like to do it like this, where I highlight these values, negative 1.5, 2, and 4. And then I just like to write above what's happening. Right here, it's decreasing, so the slope is negative, right? The derivative here is negative. Right here between these two, it's increasing, so it's positive. And then you can easily see the switch between them, right? And then negative, and then positive again. Questions? Okay. Oops. So going through these here, this is exactly what we just talked about. We have decreasing between this. That means our slope, our derivative, is going to be negative. We have increasing, so our slope, our derivative, will be positive. And that holds true for each segment that it's doing. Yes? Okay, so rather than having graphs, what does this look like with the equation instead? I'm giving you all visuals here. What will this look like with an actual equation instead? So let's move on. Let's move on to slide 9, and let's actually do one with some equations. I don't want you to graph it. I don't want you to go to Desmos. You need to be able to do this by hand. I say that because last year in AP Calculus, a number of students only ever went to Desmos to answer this question. They got beat up when it came time to do the second derivative test because they didn't understand the first derivative test. Funny how that works. And they also got beat up on their AP Calc exam they told me about because instead of being able to just get to the answer, the AP Calc exam asks you specific parts about specific steps along the way, which of course you can't do if you're not following that step way. Does that make sense? Okay, so the first thing we're going to do is determine the intervals where we are increasing and decreasing. So we need to get the critical values. So for us to do that, of course, we need to get a derivative. Yes? So let's start by getting our derivative here of f of x. We got x cubed, 3 over 2x squared. Okay, this should be a pretty easy one to do. What are we going to do here, gang? What's help me give a derivative? Easiest question I'm going to ask all day. Mark?
It'd be 3x squared.
3x squared plus
2 times the 3 over 2, which would equal
about 3x.
Yeah, 6 over 2.
3x. Okay, now what are we going to do with this? What do we want to find here? The critical value. So what are we going to do, Ryan? We're setting equal to 0. So let's pick this up. Let's set it equal to 0, 3x squared plus 3x. Now let's not overcomplicate this question. How should I go about solving this? Go ahead, Kev. Let's factor the 3x out. And that's going to leave me x plus 1. Okay? Of course, the next step here is to do what? Set both parts equal to 0. Of course, 3x equals 0. That's going to occur at x equals 0. There's one critical value. X plus 1 equals 0. That'll be at x equals -1. There's my other critical value. So, for those of us following along in slides, because I have it all pre-programmed in, everything that I did here in purple is what I did in the purple box. Identify the critical values. Get the derivative, set it equal to 0, solve it down. You get these two values. Questions here or concerns here about where we have began? Okay, now I'm going to draw my fancy little number line. I'm going to draw my fancy little number line. Well, that's no good. That's probably going to be an issue in a second. And I'm going to put my zeros on it. Negative or 0 and -1 and 0. We'll find out in a sec. Seems to be. Mr. Kaufman has not yet broken it. All right. Are we all okay with my number line? Okay? We're going to plug in some numbers and we're going to grind this out. So I want to know, is the derivative, is the slope positive or negative here? What should I pick? What's on this side of this number? Negative. Okay, so pick a number.
-2.
Okay, where are we going to put it? Into the derivative. Okay, so when I plug it in, 3 -2 squared plus 3 times -2. This is going to give us 12 minus 6. That is a positive 6 at the end, is it not? Okay, so we are positive here. So we are increasing from negative infinite to -1. So I can already say that. Okay, what should I pick between here? -0.5 sounds good to me. Let's plug that in. 3 -0.5 squared plus 3 times -0.5. Well, -0.5 squared is 0.25, so this becomes 3/4. And this is minus 3/2. I'd rather do a fraction, to be honest, gang, because I find fractions to be a lot faster than decimals at this point in time in my life. If I double this one here to make some common denominators, I'm left with -6/4, which gives me -3/4. So I have negative here, so I'm decreasing between the two values, yes? Okay, what's going to happen on the other end? What should I pick over here? 1. Don't make it overly complicated. Don't pick 2, 5, or 6. Just pick an easy one. Do 1. So when I do my next one, 3, 1 squared plus 3 times 1, I'm going to get 6. Positive yet again, right? So with my information, I can go ahead and state my increasing and decreasing. I can state maximums and minimums. I got all kinds of stuff here. So for those of us following along with our notes here, our slides, this is what we did in blue. We started plugging in some values. Oddly enough, you all picked the exact same 3 values I picked. I don't know if you're just looking ahead or common sense just dictates to pick these. I think common sense dictates these. And then, of course, that gives us how we filled in our number line. So now the last step, the green box, let's write out our increasing and decreasing intervals. So we are increasing from negative infinite to negative 1, and also from 0 through infinite, here and here, correct? We are decreasing between the two, between negative 1 and 0. Sorry.
So for an answer on a quiz or a test, you're gonna want what's in green and not like what's in black.
Oh, I'm going to need everything. Oh, I'm going to need everything. You can shorten down some of it a little bit, but there ain't much here that I didn't write that I don't need to see. You can shorten this down a little bit, but I want to shorten it too much, because if you make a mistake here, that's where I can still help you out a little bit. Luke?
So you would say that number line is the easiest way to do it?
Yeah, I think so. I think it's the best representative of it. I don't, especially when I start giving you things that have 7, 8, 9 critical values. Well, I probably won't give you that many, but at least 4, sometimes 5. I think that this works a lot better than, because if not, where else are you storing this information? In between them.
Graph, I guess.
Exactly. So you'd have to start right here. You'd have to say negative, right underneath here, you say negative infinite through negative 2 or through negative 1. You have to remember that this negative 2 doesn't actually correspond to negative 2, it corresponds to negative 1. I think that this is a much better visual way to see that information rather than anything else. Of course, you could make yourself a little chart or something like that. I mean, for those that are more straightforward data analytic type people, that's fine. I mean, some people are. They eat, drink, and breathe Excel, but it's just not me, and I think that this is an easy way to do this. I actually picked this up out of what's called actuarial science class, with the way they do time and represent time is with the line instead. Questions here? We can even go one step farther here and state maximums and minimums, and that's what my next slide is going to be about. But we could go one step farther here. Because we're switching from positive to negative, this implies that at negative 1, we have a maximum. And since we're switching from negative to positive, that implies at 0, we would have a minimum. So let's talk about that. That is going to be slide 10. Slide 10. So this is what the first derivative test really allows us to do, is, of course, look at the critical numbers. It allows us to state the intervals for increasing and decreasing. And based on these intervals, as I had on the other key information slide, we can use this to help us determine whether or not we are increasing or decreasing. So if the derivative changes from positive to negative, we must have a max. So right here, we have a max at negative 1 because we are switching from positive to negative. I can't tell you if it's the absolute or if it's relative. I just know it's a max. That's what the second derivative test will help us do. The next one here, of course, is going to be if we swap that around. If we go from negative to positive, then we will have a min. So right here, we have a min at 0. And if we want to know what these actually are, not where they are, but what they are, we can, of course, plug them back into our original. And if it does not change, which it is possible for me to flatten out, have a critical number, but not change slope after, something like a cubic function would have that, where we come up, we flatten, and then we continue on upward, then it is neither a max or a min at that point, which is what we'll talk about later on, probably tomorrow. Questions here? I am officially out of color, so this is good right here. Questions, concerns, issues, meltdowns? Anybody on chat have questions? Doesn't seem like it. Don't even know if they're still there, to be honest. They're quieter than you guys are on chat. Of course, mainly it's just John talking. That's okay. I like it though, John. I wish the rest of your gang here would get on board. I mean, like, that's the time for you guys to say whatever you want to say, because Mr. Coughlin can't actually see it. So, but just keep in mind, Miss Reed has been popping into our live sessions. Don't say too much. Don't get me in trouble. Mr. Coughlin can't afford no more trouble this year. I've already been enough. So let's go ahead. Let's do the whole deal here with this next one. Going on to slide 11. I can't think of a better problem. I've got trig in here. I've got all kinds of stuff going on here. If we can do this one, we should be able to knock the rest of them out of the park. Okay? So let's work this one out together. Okay. I know the answer to this question already. Anybody want to help get started? It's the easy part right now. Allie, we know what we need to do first. We need to get a derivative up here, correct? Okay. So we have our original f of x is equal to 1/2 x minus sine x, correct? Okay, well, this should be a pretty easy derivative to do. Derivative of the first term is, of course, 1/2. Derivative of the second term is minus cosine x. Are we all okay with this? Cool. Now, Allie, I've heard from just about everybody. The two people I haven't heard from today, I'm not sure why I haven't heard from them, but you can go ahead and pick somebody for me since nobody else wanted to volunteer. No, you choose. Let's just pass the buck off. Pick somebody. Todd. Todd, next step. Set it equal to 0, right? We need to find the critical values. So set it equal to 0, like I did last time. I'll do it again in purple. 1/2 minus cosine of x. Okay? What are you going to do here, sir? Let's send the 1/2 over. Negative 1/2, negative cosine x. Now what? Yeah, I'll drop the negatives. Okay, when is cosine equal to 1/2? Not pi over 4. Pi over 3 is what I'm looking for. What else? More than one answer here. What are the other values of pi over 3? Which one do I want? Not 4 pi over 3. That would be a negative 1/2. Go a little far. I want the ones in quadrant 1, which you already have. I want the other one that is in quadrant 4. What's the value of pi over 3 in quadrant 4? I see we're just Googling the unit circle now. What is it, Todd? Not 4 pi over 3, but what's the next one? 5 pi over 3. There it is. Okay, so we have our zeros, right? We got our zeros. At 5 pi over 3 and pi over 3, right? Let's draw our line. Let's draw our line. Pi over 3 and 5 pi. over 3. Okay? Don, we'll let you off the hook. Who's going next? Who's got the next step for us? That's the easy question, sir. Just pick somebody.
Oh, sorry.
Nobody does. That's why I'm having you guys pick. Who's going to go? John. John, we need some numbers here. What you going to put in?
Pi over 4.
Pi over 4. Pi over 4 would be right here. Okay. I think that there's an easier one to do pi over 4. How about 0? We're going to put it into our derivative here, right? Okay, our derivative has a trig function involved, right? Okay, so how about we put in 0?
Where x is at?
Yeah. This would be 1/2 minus cosine of 0, right? Okay, well that's minus 1, isn't it? Okay, so that's going to give us a negative value here, right? Now, there's nothing wrong with doing pi over 4. Pi over 4 would have been root 2 over 2, which if I wanted to do that, let's swap this out real quick for that. It'd be minus root 2 over 2, which is still a negative number, which also works because at least we do have the 2's on the bottom, which helps, and root 2 is bigger than 1. You end up with like negative 0.41, blah, 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 all over 2. Okay? So either one would have worked, John. I'm just trying to help you find the easiest value here for a trig function. Okay, what's next?
What's in between pi over 3?
Yep. Let's choose an easy one.
Pi.
Yep, I think so. Pi fits right between those. We have 1/2. We got minus cosine of pi. What's the value of cosine at pi? Come on, gang. We got to know the unit circle. That was day 1. That was day 1 in class.
1.
No, not 1. Other side.
-1.
-1. Thanks, Luke. I got minus and negative. Doesn't that become positive? So I'm looking at 1.5. So I got a plus right there. Okay, what are we going to pick on the other side of 5 pi over 3?
7 pi over 4.
We could. Sure. We'll do 7 pi over 4. That's going to give us, once again, positive root 2 over 2, which gives us, once again, the negative 0.41, blah, 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 all over 2. We're looking at another negative number. Questions here? You could have also picked 2 pi, which would have been back to 1. Okay? Going to let John off the hook now. We drew our number line. We filled it in. John, who's going next? Tom. Filled everything in. Can you tell me some extremes here, sir?
We can do like our increasing and stuff, right?
Well, yeah, but I'd rather just jump to the extreme values because that's the question here. Is where's the max, where's the min here? So negative to positive means which one?
Negative to positive, that's a minimum.
So min at x equal pi over 3. That's terrible. Let's try that again. There we go. Okay, what's positive and negative?
Max.
Max at 5 pi over 3. And if I do want to, Don, that we could go into the increasing, decreasing. We would be decreasing. This is going to be from 0 because we're not starting. We do have this closed off, right? 0 through pi over 3. Increasing between pi over 3 and 5 pi over 3. And then decreasing again, 5 pi over 3 2 pi. Questions here? Can't fill in any more information, not right now, at least. Not till I give you the second derivative test and talk about concavity. Questions? Okay, an easier one for you. An easier one for you. Moving on to the next slide, to the next problem, an easier one. Slide number 12. Go ahead and try it without me here, and we'll see if we have any questions. Just we're not going on and on and on forever. Because otherwise we don't cap it. Todd has a really difficult problem of trying to list out a series that becomes infinite. Because then the next one after 5 pi over 3 will be 7 pi over 3, and then 10 pi over 3, or no, excuse me, 11 pi over 3, 13 pi over 3. You just keep going. I will not have to worry about that for this one here. For this one here, I should be able to use it unboundedly. Should be able to go from negative infinite through infinite here for this particular question. No. Chain rule here. Chain rule here. Derivative is up there, by the way, in case you want to double check your work. My derivative is up there. Done.
Yeah, it does not exist there, so that doesn't make sense. It's just what's in that room. Right?
Yeah.
What?
You said bottom?
Oh, yeah, my bad.
Because you're like, right,
Oh, I read that as one, that's why.
they get on.
Find the derivative of that. And then once you find the derivative of that, you plug u back in. And then you times it by the derivative of u.
Yes, 4x doesn't need that. That would be correct.
So I will forewarn you all of you, both here in person and on live stream. Tomorrow is the day that I'll probably fill this board with a single problem. If not, have to erase and continue so that way everyone can continue to see it when I have to run the second derivative test. Because we get to do everything that we are doing here, plus repeating a lot of it for the second derivative. So, good talk. Let's go ahead and let's jump into it. Who wants to help? Mr. Guido, you left off with the last one. Why don't you pick somebody?
Find the derivative of this one.
Well, I can too. It's already on the board.
Yeah, but see, then I feel good about myself.
Okay, well, help me get through the derivative then, sir.
All right, so you're gonna use your good old chain rule.
Good old chain rule. I like it.
So I did a x squared minus 4 was equal to u or whatever.
Okay, so you did the whole
Yeah, like this.
u sub, okay?
Yeah, so then you have u prime is a 2x. Okay, so then you can do your like the power rule. So you bring your 2/3 up front, and you have the u times u prime.
Mm-hmm.
So
Just
then-
like that, correct?
Yes, then you plug u back in and u prime. You get the then you have 4x over. I left it as a like to the power of fraction. So
Okay, I'm gonna put it as a root though, for the time being. And then of course we do need to simplify just this numerator into a nice clean 4x, right? There's our derivative right there. Questions? Okay, so Dom, let's go to somebody else now.
all right.
Barker, next step, what do we do with the derivative?
We said equal to 0.
Equal to 0, well, that's part of it, yes. When is this going to be equal to 0?
I have no idea.
Okay, does the bottom have any impact on whether it equals 0 or not?
Oh, you said the numerator equal to 0.
Okay. Numerator equal to 0. That gives me x equal to.
I'm following that with 0. I'm so stupid.
So this is when f's derivative is equal to 0. There's another situation we need to be concerned about. Critical numbers occur at 0 and also when? When the function does not exist. So, when f's derivative does not exist. When does this happen, Parker?
Whenever there's a 0 on the bottom.
Whenever there's a 0 on the bottom. Now, do I really need the whole bottom here, or do I only need one part of this?
Only one part.
I only need this part specifically for this to go to 0. So x squared minus 4 equals 0, correct? That's going to give us x equal to
2
plus and minus 2. You do need both here. There's no limitations on this domain, so we need both values. Okay, make a number line. We've got -2, we've got 0, and we've got +2. Parker, who's up?
I picked John.
John's gone like twice. Let's pick somebody else.
Dawson.
Dawson. Next step, sir.
Just plug it.
Plug and chug, right? Okay, let's pick some good numbers then. What are we going to pick?
-3, sure.
That seems like a good number to me. So 4, -3 over 3 Negative 3, this is a cubic root, so we're going to have to pay attention to that. Minus 4. I've got negative 12. I've got 3. I've got cube root of 5. Dawson here, I'm going to make this a lot easier for you. Ready? Negative number on the top, right? Is this going to come out to be positive or negative on the bottom?
Positive.
It's positive, so I got negative over positive, which means negative overall. You like how I made that just a little easier? Okay, Dawson, new number.
-1.
Yep, that seems like a real good choice. 4, -1, 3, -1 squared, minus 4, that's a cubic root. -4 all over 3, cube root, -1 squared is 1, minus 4 is -3, okay? What are we going to have here? Of course, it's going to be negative on top again, right? What about the bottom?
Negative.
It's going to be negative. Cubic roots can send out positive and negative answers. So negative over negative means the whole thing is positive, isn't it? Okay. Dawson, new number.
1.
1. Dawson, not a whole lot going to change here when it comes to our work. Except for the top now is going to be 4. The bottom is actually going to stay the same. So I'm looking at plus over minus this time, correct?
Yep.
Back to negative. Okay, next one.
3.
3. 4, 3, 3, cube root, 3 squared minus 4, 12 over 3, cube root, 5, plus over plus, looks like plus to me, right?
Yep.
Okay. How's everybody doing? This is the part of class where anybody that ever doubted that Mr. Kaufman can do math quickly has to eat words. Dawson, answers here. First, let's catch everything up here for our slides, for anybody that's following along here. So we got our blue square here, which was our finding our values here. So blue, I went purple on mine. And then we did our number line, and then I filled that in with my given answers here. So we should be able to state our maximums and minimums now, sir. So where do we have some maxes at? Let's start with maxes. At x equals 0. Any other ones? No, because it has to go positive to negative, okay? What about mins?
-2 or plus minus.
X equal positive 2, x equal -2. Let's separate them here. Well, yes, you could do plus minus. I think it's just best interest to separate them because like the chances of both of them being a min is pretty low. Questions here? Okay. Anybody want to take a shot at doing the increasing, decreasing intervals here since we're running low on time? Dawson, why don't you pick somebody, see if we can get them up here.
Who hasn't done yet?
Pardon?
Who hasn't done yet?
Anne Marie, Caleb. I don't think I've heard from Caleb all class.
Take it away, Taylor.
Caleb, let's do some increasing, decreasing intervals up here. Where are we decreasing from?
Decreasing from negative infinite to -2,
Let's do all the decreasing intervals. Where else?
and from 0 to +2.
To positive 2, okay? And then our increasing intervals.
-2 to 0 and 2 to infinity.
Very good. And that's it, gang. That's everything I've showed you here. That's everything I've showed you. Now, if you want to know the actual extremes, you do need to put these points back in. For us to actually know this, you need to plug -2 back into the original to figure out whether it is a maximum or minimum. And it is 0. What that value is, not where it occurs. This is where the actual values here, of course, these two will be 0 when you plug them back into the original. You get 0 in here, which means the whole thing goes to 0, right? So the minimum here is 0. The maximum here when you plug this back in is going to be a little bit more complicated. You're going to get the cube root of 16. Questions here. So do pay attention to that, because I've asked find the relative extreme. That doesn't just mean where are they, it does also mean what are they. So right here for this part of our answer, we do need to fill this in with 0, cube root 16, and these are 2, 0, negative 2, 0. Questions? Issues? Okay, I wish we had time for our next one here, but we don't. The only thing I can tell you here about slide number, 13? Slide number 13 is when you go for this one here, when you start setting up your derivative, you need to be careful. F of x does not exist at 0 because it has a vertical asymptote, which means that it's not differentiable at 0 either. So it can't be a max-min point because it is not either of those. Okay? Now, it's very possible that we'll switch from positive to negative there, but that doesn't mean that we have a max-min. It could be one other thing that we'll talk about tomorrow, which is concavity, which helps us determine whether or not we have a max-min or a vertical asymptote. And that's all the more we got time for here. Unfortunately, we are running low. We're looking at page 186 for our homework here. Page 186 for our homework here. Slide at the very end has our homework on it. So that's us on our live stream. Hope we all did well. To the two of you that responded to that question earlier, thank you. And I'll see you all some other time. The rest of you guys copy down your son. Let's go ahead and let's start backing up. Those of us on our live stream, let's go ahead. We can log off. And I'll see you all tomorrow morning. Well, you'll see me. I won't see you. I'm done for today. No sleep left to play on done. Before we all go, I do have one more thing to talk about with, which I discussed before, but I'm going to go ahead and reiterate it again. We're getting too close to our work being too similar. There's 2 or 3 of you in particular that I have some issues with. Now, I'm not going to call us out like I did on stats, not yet. It hasn't gotten to that point. But you need to be honest with me about whether or not you're doing your work by yourself or you're using somebody else's work, what it is. This is your only and last warning about it. If you think calculus is hard now, or if these problems are difficult now, wait till you have a time limit. So, be honest with me about where and what work you're doing. Okay? And hopefully this doesn't become a bigger issue.